Hello, so today I'll be going through a bit on the chemistry of alkenes and alkynes. So I'll first start off with a bit of frontier molecular orbital theory. So I'm sure that all of you have heard of Zaitsev's rule before, which is that the more substituted alkenes and alkene is, the more stable it is, right? If alkyl groups directly bonded to the CC double bond, stabilizing the molecule. So why is this so? We have to take a look at the molecular interactions that are actually occurring. So we notice that one of the CH bonds, right, of say a methyl group at the site is able to actually have the right geometry to interact and overlap with the pi or rather the pi antibonding orbital of the CC double bond. So why is this? So this is because if you were to see what is the geometry of this carbon here, right, it will be tetrahedral, am I right? And what will be the geometry of the pi star antibonding MO? It would be in such a way that the two p orbitals forming the pi bond is overlapping in a way that's out of phase, right? And so these two molecular orbitals can actually undergo a quantum superposition to form a resultant bonding molecular orbital and an anti-bonding combination. So we realize that because one of the orbitals contains a pair of electrons, right, which is this one, the bonding orbital of the CH sigma bond, right, and one of them is an empty anti-bonding orbital, right? So the overlap results in the occupation only of the constructive interference molecular orbital, right? The in-phase molecular orbital. So resulting in overall stabilization of this amount of the energy, right? And so this is a form of a delocalized bonding. Why? Because the electron density in the CH internuclear region now shifts over to this CC internuclear region, right? Because we expect that the resultant molecular orbital formed from the interaction of these two MOs will have a non-zero coefficient, right, on this carbon atom over here. And we do know that we can represent delocalization of electrons in a separate theory of bonding called valence bond theory. And how we do that is through drawing resonance structures. So what will be the sort of resonance structures we'll be seeing, right? So what do we observe? We observe that the CH bond, right, loses electron density, suggesting that the CH bond, right, breaks, right? We also realize that the anti-bonding orbital of the CC pi bond is now being filled in a sense, right, being attacked. So the CC pi bond is expected to also weaken. And so you can illustrate it by drawing a resonance contribution which has a broken CH bond and a broken CC pi bond, right? And what do we have? We have a double bond over here. So this exists in resonance with this structure, right, giving an overall structure where it agrees with actually the molecular orbital picture of it, which is a weakened CH bond, right, a strengthened CC bond over here, and a weakened CC pi bond over here. And because we know that resonance, right, always results in energetic stabilization, correct? So that is the valence bond theory way of explaining how hyperconjugation brings about stabilization, right? So as you can see over here, this would be the two resonance hybrids. So now that we have explained why more substituted alkenes are more stable, we can go on to take a look at the electrophilic addition of alkenes. So I'll skip what you have already learned probably at the junior college level about electrophilic addition of alkenes, and in fact go on to some more interesting aspects of it. The first aspect will be Kabocha rearrangement. Now if I were to tell you that I react, right, this alkene over here with HBr, right, what will you get? You would immediately tell me, right, most likely that you will get this resultant product, right? But however, what if I tell you that this one is only the minor product, and the major product is actually this bromoalkane? So how would you explain how this occurs, right? So we can explain this by a carbocation rearrangement via a methyl shift, which is a shift of a methyl group. So as you can see over here, the double bond, right, is attacked by a positively charged hydrogen, and thus resulting in a carbocation being formed. But notice that this carbocation is a secondary carbocation, right? Whereas if a methyl group were to shift over, right, to the neighboring carbon, which is possible, right, because it's just one carbon away, we can get a tertiary carbocation, which is significantly more stable. And then it is this carbocation that is formed and that is attacked by the bromide to form this bromoalkane over here, which will be the major product. Another example of carbocation rearrangement is if the original carbocation has an unstable ring structure, say if it has a 3-membered ring, right, or even a 4-membered ring, right, whereas a carbocation rearrangement can result in the formation of a more stable 5 or 6-membered ring. Then there is also a driving factor in causing the carbocation to rearrange itself. So that is quite important when you want to propose the mechanisms, right, and explain, and sometimes the question will ask you to explain why the carbocation rearrangement is favorable. So you can think of the stability of the positive charge, or you can think of whether it results in the relief of some ring strain. So let us now take a look at the second thing, which is the bromonium intermediate. So normally, if I were to have a alkene and I were to add Br2 to it, correct? What would you observe, right? You would expect this cationic intermediate to form, right? Sorry, the bond is no longer there. Correct? And then what happens? Notice that this, right, is a planar carbocation. So the bromine can attack from above or below the plane, right, giving a racemic mixture. And if it was say a cycloalkene in that sense, then addition of Br2, right, because we eventually get a let's say the bromine attacks from the bottom over here, and then get a positively charged cationic intermediate over here, we realize that the bromide can attack from above or below the plane, right? So giving rise to two possible products, correct? If this mechanism were to be correct, right? Both the anti-addition product and the syn addition product, correct? However, this is not true. We observe that only the anti-addition product is actually observed, or the syn addition product has very minute quantities and in fact is not observed. So why this is so, and how can we explain this? This can be rationalized by the fact that there's a bromonium intermediate. So when the CC double bond, right, the pi bond attacks the bromine molecule, right, what is formed instead of a carbocation is a bromonium ion, where there's a link bridge formed by the fairly large electron cloud of the bromine atom, correct? So this is the bond that is actually formed. So you can think of it as a positive charge being localized on the bromine atom, and so it is afterwards that attack of the Br minus results quite similar to epoxide opening, right? The attack of this bromide anion causes this CBr bond to break, thus forming an anti-addition product. So the reason for this is that the bromide ion can only attack from the other side of the CBr bond, right? You can think of it as attacking this side will be repelled, right, by the large electron cloud of the bromine atom that is in the bromonium cation. Or I can think of it as, because we want to break this CBr bond, right, so we want to attack the anti-bonding orbital of this CBr sigma bond, and its major lobe, right, will be facing in the opposite direction of the CBr bond, correct? So the result is an anti-addition product. So that is why the syn addition product is not really observed. So we learned that actually all this discussion, right, was talking about the Markovnikov addition, correct? So where we expect that the hydrogen atom will attach to itself the carbon, which already has the greater number of hydrogen atom, right? And this is explained by carbocation stability. And however, carbocation stability, right, can result in anti-Markovnikov addition. So now we are not disobeying the rule that the more stable carbocation is favored. We are disobeying the rule that the Markovnikov rule that the hydrogen is added to the carbon which has more hydrogen atoms bonded to it. So why this is so? This is because of a differing mechanism. So as you can see, one example is hydroboration, which is addition of H2O using a BH3 catalyst. So how this occurs is that first there's this attack of the boron atom by the pi bond. Why? Because the boron atom is electron deficient, right, having an empty p orbital, and then thus forming this intermediate over here. And note that the steps of this first step actually is actually there is another intermediate form, correct? There's this intermediate actually being formed, and note that this intermediate is formed, right, instead of this intermediate because of carbocation stability. So we are going back to the same principle of carbocation stability, right? So this one is formed, thus resulting in the formation of this intermediate, which is then oxidized by H2O2, right, to form the BH2 is oxidized to form an alcohol group. So that is why the alcohol group is actually on the less substituted carbon atom, and whereas the hydrogen is gone on to the more substituted carbon atom. So we are not defying the idea of carbocation stability, but in fact utilizing this idea of carbocation stability with a different, more longer mechanism to yield a result that actually seems to go against Markovnikov's rule. So another example for anti-Markovnikov addition is free radical addition, right? So in this free radical addition, right, so we are having we're adding a peroxide. So this can be an organic peroxide as well, or it could be hydrogen peroxide. So you do know that the oxygen-oxygen bond in a peroxide is extremely weak, and so it is easily broken off to give, in this case, hydroxyl radicals, right? And these hydroxyl radicals can then take a hydrogen atom off from HBr, right? Sorry. Correct, to form what? To form water and a bromine radical. So why is the hydride radical not formed? Why? Because the hydride radical is highly unstable. Okay, so instead it is the bromine cation that is the attacking species. And so, right, we have two options over here. Correct, we can either form, okay, let's say there's a methyl group over here. We can either form this, or we could form this, right? So which is more favorable? We do learn that the more substituted radical is more stable, and this can once again actually be explained. Sorry, this can once again be explained through the idea of hyperconjugation, but I won't talk about that over here. But anyways, we do know that this radical is more stable, and thus this radical will be where the this carbon atom will be where the unpaired electron will be, and where it can attack, right, another HBr molecule to form this anti-Markovnikov product, correct? Right. So this, the Markovnikov product obeying Markovnikov's rule, right, will not be produced. So this shows that Markovnikov's rule is just an empirical observation that only applies for a particular set of particular family, I could say, of reaction mechanisms, right, where it follows a certain pattern, and because of carbocation stability rules, right, Markovnikov rules is the eventual observed result. But note that for these two cases, right, the product is anti-Markovnikov in nature. So another reaction of alkene is the addition of carbene to alkenes, right? So okay, there is different mechanism whether the carbene is in the singlet or the triplet state, but for now we won't discuss. We'll assume that the carbene, right, has a lone pair of electrons, right, instead of two separate unpaired electrons held in two separate orbitals, okay, and then forming this cyclopropane ring. And then of course you can also have an attack on the cyclopropane ring in subsequent steps as well, right, similar to an epoxide ring opening. But as you expect, right, carbene is highly unstable, right? So normally you want to generate the carbene in situ, or generate a carbene-like reagent, right, that achieves the same effect. So how this is normally done is through the Simmons-Smith reagent, right, where the iodoalkane, right, is actually reacted with zinc in the presence of a copper catalyst, right, and to form this in situ, and this then reacts with the alkene, thus achieving the same effect of creating a cyclopropane ring. So it makes sense to you, right, because the Ci and the CZN bonds are likely to be very weak, correct? So effectively, this behaves as if it is a carbene. Okay, so there's now I'll talk about mild oxidation of alkenes to diols. So other than KMNO4 method, there's also two other methods. The first method is osmium tetroxide, right? And so this gives a syn product. And the second method is through M-chloroperoxybenzoic acid, right? So it's M because the chloro is on the not on the ortho position, not on the para position, but on the meta position, right? So meta chloroperoxybenzoic acid because it's a peroxy acid. So peroxy acids are normally highly reactive. So I won't go through the mechanism of formation of this, even though it is very interesting and you can read up on it. But basically, it forms an epoxide intermediate, and this epoxide intermediate is then opened in the presence of acid or base catalyst, right, to form an anti-product, right? Why? Because in order to break the CO bond, right, the hydroxide must attack from the other end, correct? Once again, using the same principles I said before, the anti-bonding orbital, right, of the CO bond, the sigma star orbital, has one of its main lobes pointing towards in the opposite direction of the CO bond, right? And so resulting in an anti-product, whereas the mechanism for the osmium tetroxide oxidation will yield a syn product. And we can also further react these the diols that are formed, right, with periodic acid to actually fully cleave, right, the CC bond to form two carbonyl compounds. And so yeah, this is basically in a sense like further oxidation, right, through periodic acid. So let us take a look at one-step direct cleaving of the CC double bond in addition to the KMNO4 that you already have learned, right? That is actually not the best method. Why? Because you get the most oxidized product, which is the carboxylic acid, right, and ketones, right, instead of aldehydes and ketones. So however, if you were to use ozone, right, we have the there's actually an intermediate, right, an ozonium intermediate. Correct, there's an intermediate that looks something like this. I need to check the mechanism, right, to like double check how it works, but if I'm not wrong, it goes around like this. And so we have two options over here. One is a reductive workup. So in the presence of a reducing agent, for example, zinc is an example of reducing agent that can be used in this case to result in, of course the ketone will always form, right? But in this case, you'll form an aldehyde instead of a carboxylic acid. But if you use a oxidative workup, right, say you use H2O2, Alright, it's one example of oxidizing agent. You'll form the ketone. Instead of forming the aldehyde, what will you form? You will form the carboxylic acid.